You're only watching this video to have a better understanding of the JT effect, hydrocarbons with their boiling point, dew point, and freezing point, how pressure affects a liquid, and how pressure affects a vapor. You need to go and watch the video on refrigeration loops. LNG stands for liquefied natural gas. LNG consists of methane and ethane, although it's mostly methane. So that would be your C1 and C2, your lightest of the lights. Right? NGL, on the other hand, stands for natural gas liquid. So those kind of sound the same. LNG, liquefied natural gas, and natural gas liquid. Both of them are liquid natural gas. One is LNG is methane, ethane. NGLs are your heavier hydrocarbons liquefied. So your C5+. They're your heavier ends of your natural gas composition, right? In the refineries, heavy hydrocarbons are going to be your C30, C50, C70. LNG, we're dealing with pipeline gas only. So that would be what comes out of the very tip top of the crude oil fractions. The dew point of LNG is negative 260 degrees. What an LNG facility does is remove any moisture, remove H2S, CO2, etc. because environmental purposes, it can corrode our aluminum heat exchangers. We remove all that, we remove the moisture because we know that water freezes way before it gets to negative 260 degrees, which is the dew point of LNG. So that would end up clogging our aluminum exchangers when we're trying to get down to that temperature. Our heavier hydrocarbons, we know heavier equals higher. What number's higher? Negative 200? So easier to achieve. Its freezing point is also going to be higher. If we kept our heavier hydrocarbons, our NGLs, in our process, by the time we got to negative 260, which is the dew point of methane, ethane, we would freeze our NGLs. If we freeze our NGLs, they're going to clog up all our exchangers in our process, right, and affect our heat transfer, etc. Yes. We have a warm end that's going to be cleaning it, removing all the H2S, CO2, moisture, etc. We go to the NGL section. The NGL section, that's where we go ahead and start cooling. When it gets into the NGL section, it's going to go and start getting cooled to negative 120 and so forth and so forth. As we're cooling in that process, we're condensing our NGLs and then removing them, our heavier hydrocarbons. So we're condensing our heavy hydrocarbons, which then become NGLs, remove them before we go to our cold end, our cryogenic unit. We're going to go over some of the different things that are used specifically to cryogenic units. Cryogenic is negative hundreds temperature-wise. One of the things is a cold box. So a cold box is a heat exchanger. It has multiple different process streams going through it. Sometimes 3, sometimes 4. One of those is going to be the gas that you're trying to get colder. The cold box is made out of aluminum. Aluminum is more efficient for heat transfer. Also, it is more resistant to damage from cryo temperatures. This isn't going to be exactly the same in every process. The cold box is going to look like a big box. It could be rectangular shaped, going up real tall, or square shaped. Ours at the plant I worked at had all the streams coming in and out of the front. So it looked like a cluster bomb until you got very familiar with your unit. The video I'm about to show y'all explaining one has streams going in and out on both sides, top and bottom. I know some of the cold boxes in cryo units with refineries and chemical plants, they're going to look more like this.
Exchanger through the feed gas inlet, flowing directly into a distribution header. The header evenly spreads the fluid over the core to ensure maximum heat transfer. Cold side streams called refrigerants enter the side of the exchanger through cold inlets and flow into distribution headers for their respective modular sections of the exchanger. Each modular section is made up of a series of layered parting sheets and corrugated fins that have been welded together. The refrigerant is directed through the heat exchanger by the fins until they reach their respective hot outlets. Sidebars prevent the fluid from mixing between the sheets. The corrugated fins direct the feed gas flow into a vertical pattern, while the fins for the refrigerants flow in a horizontal pattern that achieves a cross-flow between the warmer feed and the cold refrigerants in each modular section. As the feed gas flows down the exchanger, it is further cooled until it achieves the desired temperature for liquefaction. The resulting cold feed gas vapor exits the exchanger and flows to a JT valve, where it changes to a liquid. The hotter vaporized refrigerant exits the hot outlet to be returned to the...
So the inlets and outlets, where they're coming from and where they're going, that's going to be process specific to a specific plant and a specific unit. That's not necessarily where it's going to be coming from or going at a unit you end up at.
Refrigeration system for compression or cooling before returning to the exchanger. Depending on the configuration, several flows can run through the heat exchanger concurrently to increase heat transfer efficiency and further cool the feed. The number of layers, type of fins, and stacking arrangements can vary depending on the specific design and application of the exchanger.
So, oftentimes cryogenic units are going to have an expander compressor. Specifically, LNG is always going to have an expander compressor somewhere in their process. We're going to talk a little bit about turbines because y'all should all be aware of how a turbine works and what it does. We're going to correlate that to help you understand what an expander does. Steam going into the turbine, it's high pressure, and then it uses its energy when it catches the buckets or chevrons of the rotor of the turbine, forces it to rotate, and it comes out lower pressure. So the opposite of compression would be expansion. So when you compress, the pressure goes up and it gets closer together. When you expand, the pressure goes down and gets further apart. A turbine, a steam turbine, essentially expands the steam. What happens to the temperature of the steam as it leaves the turbine? How does pressure affect a vapor? Lower pressure, lower temperature. Is a turbine essentially overall, looking at it from a way out lens, this isn't the purpose of a turbine. In general, a turbine expands steam. It's not the purpose. The purpose of a turbine is to drive rotating equipment. Now, resistance on that rotating equipment, this is your shaft, goes in low pressure and comes out high pressure. So a turbine is going to drive it. This is your shaft, this is your compressor. The resistance of having to move this and increase the pressure is what's dropping the pressure of your steam. Now, we know that LNG, because I highly recommend watching the refrigeration cycle if you don't know what the JT effect is and how pressure affects a gas and how pressure affects a liquid. We know that the JT effect is rapid drop in pressure equals rapid drop in temperature. An expander works almost identically to how a turbine works. You know how you can have two identical shell and tube heat exchangers. Let's say they're both U-tube. This one has cooling water going to it. Now this one down here, exact same size, exact same design, it has steam going to it. We're going to call one a heater and one a cooler or a condenser. They're identical. The name of it is based on its purpose. We want LNG, the goal is to drop the temperature of our process so we can get it to the dew point, or drop the temperature of our NGLs so we can get them to the dew point or remove them from the process. Okay, so the expander, the purpose of it isn't to drive like a turbine. The purpose of it is to drop the temperature of our gas further. We want to expand because expansion is dropping your pressure. How does pressure affect a gas? Lower pressure, lower temperature. What is the JT effect? Rapid drop in pressure equals rapid drop in temperature. So instead of like a steam turbine, you have steam going in, we send our process through it. Our feed going into our expander is going to be our natural gas process. We're going to go in, it's going to use its energy to rotate the buckets, our runs on the rotor. The resistance is going to be this compressor. As it's using its energy, it's going to drop its pressure. It's going to expand. Then it comes out, natural gas, I'm going to just put NG, it's ugly, get the point. Natural gas, but the temperature is going to drop drastically because we're creating the JT effect. Why waste that energy? We just used. So we'll go ahead and drive a different part of the process. Go ahead and compress it. When our expander is down, this thing is massive. It's probably 2 or 3 of our classrooms. Very big, very expensive piece of equipment. We're not gonna have 2 of them in the same unit. We're not gonna have a standby in case something goes wrong. So around that, if our expander's down, we have a JT valve, which stands for Joule-Thomson. To help you further understand the JT valve, go watch the refrigeration videos. The JT valve we can use if there's something up with our expander. What it does is restricts flow. We know if go watch the videos if you don't understand. We know if we restrict flow, our pressure's going to drop downstream of that flow restriction. Again, when it goes through here, this is going to restrict flow, our pressure's going to drop. When our pressure drops, we're creating the JT effect. Rapid drop in pressure equals rapid drop in temperature. It's not as efficient as the expander. We can still proceed with process if the expander is down. After we remove our NGLs, we're going to go to our cold end, which is where we're going to actually cool our methane ethane to negative 260 to reach its dew point. We used MRPR, mixed refrigerant, and propane. C3MR, MRPR. We had a bunch of mini refrigeration systems that were going, and the refrigerant was going to our MCHE, main cryogenic heat exchanger. I'm going to refer to it as the niche for now on. To give you an example of how big this thing is, this is a human. This is our main cryogenic heat exchanger on our trailer getting ready to get installed. When I tell you this bad boy is a tube cluster, it is a tube cluster. It's spiral wound. There's multiple different streams of tubes. So you can see here all the different streams that are going in and out. The very tip top is going to be our actual LNG leaving. So our MRPR is going to be coming in, going through tube. Some of it is going to go out and go to a JT valve. If you're not familiar what a JT valve is or the effect it creates, I recommend watching the refrigeration video. From the top of this, it's going to go to our LNG tank, and from there, ships are going to be coming to load the ship with LNG. They're going to be traveling across the world. Why do we do this? Other countries don't have the supply of natural gas like we do. So we send it over there to them so they can use it. We know that when you condense something as operators, or now that you've been going through the program, we know that to condense means to turn a vapor into a liquid. But when we turn a vapor into a liquid, we have to cool it. We also know about thermal expansion and thermal contraction. Thermal expansion, when you heat something up, it gets bigger, it expands. Thermal contraction, when you cool something down, it contracts, it gets smaller, it condenses. When we turn a vapor into a liquid, we actually make it take up much less space. Methane, ethane in gas form versus liquid form. It has a 600-to-1 volume ratio. This is a very important note to know. It has a 600-to-1 volume ratio. What that means is for every 1 LNG ship liquefied, you would have to have 600 ships of methane, ethane in vapor form to be equivalent. We liquefy it because it's efficient. That's the most efficient way to send it across the world. The countries that don't have the supply of natural gas, they need it for heating their water heaters, their stoves, to cook, etc., etc. When it gets to where it's going to a specific country, they actually have LNG regas facilities. All they do is vaporize it, turn it back to a vapor, and then they send it to be used. Most important 3 things you need to know for an interview, if you're interviewing for LNG facility. The countries need it. They don't have the infinite supply like we have. They need it for cooking or heating, etc., etc. What an LNG facility does is they cool it to its dew point, which is negative 260 degrees Fahrenheit, to condense it. And why do they do that? The 600-to-1 volume ratio. You can ship 600 times more in liquid form than you can in vapor form. When it gets to the other part of the world, wherever they need it, they turn it back into gas and use it for their needs.